Hello guys, welcome to today's class at Math Studio. Today we're gonna work a mathematical proof by induction of a quadratic series. It is given by the sum of integers from r equal 1 to r equal n of r squared, which is equal to n over 6 n plus 1 times 2n plus 1. The first thing we're gonna do, which is step 1, is to let n equal 1. So when n equal 1, p of 1 will be equal to the sum of 1 square, because we put 1 into r square, equal to 1 and 6. So we're gonna put 1 wherever you see n on the right hand side. So this will give you 1 plus 1, 2 times 1 plus 1. So our aim is to try to get 1 on both the left hand side and right hand side to prove that step 1 is true. So this would give you 1 equal to 2 times 3, which is 6, and 6, which is equal to 1. So therefore p of 1 is true. Our next step is to assume true for n equal k. And we call that p of k, which will be equal to the sum of integers from r equal 1 to k, which is equal to, so now we're going to put k wherever you see n on the right hand side. So now you would have k and 6, k plus 1, 2k plus 1. Then we're gonna say that since we assume p of k is true, what we're gonna do now is try to prove that k plus 1 is true, n equal k plus 1 is true. So then p of k plus 1 would be equal to the sum of integers from r equal 1 to k plus 1, which would be equal to, what you're gonna do now is let sum of k plus 1, n equal k plus 1, equal to p of k plus the last term that you will get from this expansion of k plus 1, and that would be k plus 1 squared. So let's rewrite that by plugging in p of k, which we got up here. This would be equal to k and 6, k plus 1, 2k plus 1, plus k plus 1 squared. Okay, and then we'll try to further simplify that. We want to get it in the simplest form possible. So now what we're gonna do is expand this k plus 1, which will give you okay, and then now we see that on both sides of the plus sign we have k plus 1, which is a common factor. So now we can factor out k plus 1 along. Can factor out k plus 1. So let's factor out k plus 1. So that will leave us with k and 6, 2k plus 1 plus k plus 1. Okay, so let's continue. What you're gonna do now is multiply throughout 2k plus 1 by k and 6, because what we're trying to get inside this bracket, we see that we have a form of quadratic equation coming up. So we're trying to simplify it, we get it into that form so we can factorize it. So let's expand this. This will give us 2k squared plus k and 6 plus k plus 1. And let's put that k plus 1 on 1. Okay, so we're gonna LCM now. This will give us all on 6. So 6 into 6 gives us 1, and 1 times the numerator will give us back the same thing. This 2k squared plus k plus 1 into 6 is 6. 6 times the numerator will give us 6k plus 6. So now what I'm gonna do here, because the 6 in the denominator is a constant and we're trying to get a quadratic equation, I'm gonna shift this outside of the bracket and put it under this k plus 1 here. And shift it out, because the k plus 1 and the larger bracket is multiplying, so you can just shift it out. So let's put it here. So what you will have inside the bracket now is 2k squared plus 7k plus 6. Okay, so now we have a quadratic equation. So now to factor the quadratic equation, which is rather simple, you should know that, but let's go through it. So you need two numbers. When you multiply 6 times 2, you get 12, and when you add them, you get 7, which is 4 and 3. So what we're gonna do is that 4 and 3 is replace the 7k here. So we will get 2k squared plus 4k plus 3k plus 6. And we're going to factor out the common term on both sides of the plus sign. So this would give us, we can factor out 2k from here and factor out 2k from here. This would give us 2k, give us k plus 2, plus we can factor out 3 from here, so give us 3k plus 2. So the answer, guys, now would be k plus 1 and 6, k plus 2 and 2k plus 3. And this is the formula for pk plus 1 when n equal 1. So what they're saying here, guys, is when n equal 1, like how we use, when n equal 1, we do use this formula for k plus 1. So let's go and write a statement which we should always write at the end of an induction. It's like a conclusion. So let's write it. Since P of n is true when n equal 1 and if P of k is true, then P of k plus 1 is true also, and because of that being true, P of k and P of k plus 1, then P of n is true for all positive integers. Which can write the C down. And that's it, guys, for our question on the quadratic equation of R squared. Thank you for joining us, and see you again in our next video at Math Studio. Good night.